All right, so in this video, we talk about complex numbers, and this is a continuation of a series of previous videos that talk about how uh, locus is involved um, in the concepts of complex numbers, and especially when we use locus when it comes to Argand diagrams. Last time around, we said that um, if in any situation we had the modulus of z1 minus z2 uh, and that equaled to a constant k, um, we would essentially get a circle where this right here would be, whoops, just the z2 would be the center and k would be the radius of a circle. And we also talked about inequalities involving those. So those are the things we've discussed in the previous videos. This time, we talk about sort of a similar concept, again, involving locus and modulus and whatnot. And except this time, we'll be talking about a slightly different situation in specific terms. So remember what we meant by the modulus of z1 minus z2. Well, simply put, the modulus of z1 minus z2 represents the distance between the two complex numbers z1 and z2. Or, in other words, z1 minus z2 is the length connecting these two complex numbers. Now, let's say for our instance, we say, look, um, modulus of z1 minus 1 is equals to modulus of z minus 1 is equals to modulus of z minus 2. So this is an example I want to start off with. And I want you to just pause and think about what this particular notation or equation means in sort of literal terms. The modulus of z minus 1 is equals to modulus of z minus 2, where z is a missing complex number, and we really don't know where z possibly is. So take a moment and think about this. Now, if you understood this concept properly, I think you should be able to understand this literally translates to this, or, in a way, translates to this. The distance of z from the complex number 1 is equal to the distance of, again, the same z from the complex number 2. Here, 1 and 2 are complex numbers. These could have been I and twice I as well. But this is an example that we're looking at. We will look at other examples, but I hope this makes sense to you. Now, if I were to ask you to, just like previous examples where we gave you an equation and asked you to draw the locus on an Argand diagram, if I were to do the same for, if I were to ask you to do the same for this equation, how would you go about doing it? Well, we would obviously need our axis, the imaginary axis and the real axis over here. And we would definitely want to start off with these complex numbers 1 and 2. Remember, the minus is part of the format. So the complex numbers involved are essentially z and 1 and 2. So let's mark where 1 and 2 are. So approximately, this, if this is 1 and this is 2, well, not the best, oops, oops, not the best diagram here, but let's say this was 1 and this was 2. And and now, based on this expression, this equation, and what we've just written, I ask you to think of one possible position of our missing complex number z. If you think about it, z has to be somewhere where its distance from this guy is equals to its distance from the number 2. So I think the obvious answer should be this point over here. That is right in the middle of 1 and 2. And however, if you do think very deeply about this, this isn't the only possible point. This point is definitely a possible point, but this isn't the only possible point. If you think about it, what if I went right above or right below this point right over here? These are also two possible points that fit this criteria. I mean, if you think about it, the distance of this point from 1 should be equals to distance of this point from 2. Likewise, the distance of this point from 1 should be equals to the distance of this tiny little red dot from 2. So if that's the case, and if you think about it, there should be multiple points, an infinite number of points that go through this middle point over here. And by now, you should be getting the feeling of what this is starting to look like. Well, this is starting to look like a vertical line that goes right through the middle of 1 and 2. So this right here, this line, and it's going to be a vertical line, this right here is our locus of points. This line over here is our locus of points containing all the possible uh, values of our missing complex number z. Because if you think about it, any point on this line, any point on this vertical line must be equidistant, as this particular question says, or situation says, equidistant from this point and this point over here. And by now, you should also be getting the feeling that this right here is an example of what we call the perpendicular bisector. So this is an example of a perpendicular bisector. In this specific situation, we had to draw the perpendicular bisector of the line joining our two known complex numbers 1 and 2. And from this example, and we will see in later examples that we can indeed generalize situations like this and associate perpendicular bisectors to situations like this. And again, I want to show you another example, this time slightly different and slightly more complicated. And hopefully by the end of this example, you should be able to understand what this is about. So the second example, let's look into another question where modulus of w minus one complex number is equal to modulus of w minus some other complex number, 2 plus 5i. And I ask you to draw the possible positions of our missing complex number w. Right. So if I asked you to uh, do this, you would obviously have to start with your Argand diagram. And that means our axis, the y-axis, which is called the imaginary axis, and the x-axis, which is our real axis. And the first thing you want to do is point out where our known complex numbers are. And just like in the examples of circles, make sure that the negative is outside the whole of complex numbers so that it is ensuring that the negative is part of the format. And we discussed the importance of this in the previous video, so you might want to check it out if that's unclear to you. But anyways, for this, let's figure out where these points are. So 1 on the x-axis, and I need up to 5 on the y-axis. So that's 1, 2, 3, 4, and let's say this is 5. So 1 plus 2i is right over here, and 2 plus 5i is right over here. And apparently, W, and hopefully by now you've understood that this should translate to something like W is in a position such that its distance from 1 plus 2i is equal to that from 2 plus 5i. In other words, W should be equidistant from these two complex numbers. So hopefully by now you've understood the relationship between this equation right here and the translation that I've just mentioned. So in other words, W is supposed to be equidistant from these 2 points. So let's say, again, um, one of the possible points of W could be somewhere right in the middle of the line that is connecting these 2 points. But just like the previous example, it could be this point as well, as long as this distance is equals to that. But it could be this point as well, could be this point, could be this point. And by now, you should be getting the impression that we have another line forming. But this one is not exactly a vertical line, but it is definitely a straight line. Whoops, that is not the straightest of lines, but hopefully you have gotten the idea. So I'm going to erase this. I'm going to attempt to draw a line here. So yeah, here's my ruler, and hopefully that is a better line. Hopefully that is a better line. Oops, no, I don't need that. But that right here. All right, I'm gonna try to complete this. I'm gonna extend from this point. Whoops, this isn't working out as expected. But well, what's going on? Oh, right. So this is what I was talking about. So we have a line that is approximately going right through the middle of these two complex numbers. In other words, the green line, which is in this case, the green line becomes in this case uh, our possible positions of W. And we say that the green line is obviously the perpendicular bisector of the line joining the two complex numbers. So any point that is on the green line is a possible position of W. And in your exam, you need to use the services of your ruler and pencils and compasses to draw this perpendicular bisector. So I hope you know how to do that using a compass. And if not, hopefully I will take the time to make a small video for this. But uh, there are lots of resources online showing you how to draw a perpendicular bisector using compass. So make sure you are well aware of it. Bisector using a compass. All right, it's a very easy process. But I hope that the takeaway from this video is the connection between uh, equations like this, where you have modulus on both sides and an unknown complex number, the same unknown complex number on both sides of your equation, and how that relates to the how that translates to the perpendicular bisector that we have drawn in this case and in this case. And the whole idea, again, in summary, is based on the idea of points being equidistant. In this example, understand that Z is essentially equidistant from these 2 points. In this example, W is equidistant from these 2 points over here, and thus perpendicular bisector. So in the next video, we will look at a few other examples of perpendicular bisectors, except using inequalities. Thank you for watching.